Okie dokie, time for the experimental design FRQ number 3, aka my favorite, because it's the easiest one to get partial credit on. If you have not yet checked out my how to get partial credit on your lab FRQ video, you should check that out. Link is in the description. Anyways, so in experiment 1, students are asked to collect data that can be graphed to determine the inductance L of an inductor. So we want the inductance, check. The students have access to multiple charged capacitors. All right, so we are able to change. That's going to be important. We are able to change capacitance, check. Each of different known capacitance and a voltmeter that measures potential difference as a function of time. So we are able to measure V of t. Okay, in each trial, the inductor is connected to a charged capacitor and an initially open switch as shown in figure 1. We have our capacitor, an open switch, an inductor. Indicate quantities that could be measured by the students that would allow them to determine L1 using a linear graph, and briefly describe a method to reduce experimental uncertainty. Okay, so we want the inductance, we're able to change the capacitance, and we're able to measure the voltage. If we roll over to our handy dandy equation sheet, the thing that relates those, in case you have no idea, so all of our inductor equations are down here at the bottom. So we have tau, which is for LR circuits, but this is an LC circuit. So we're probably going to want to use this guy right here, omega LC equals 1 over root LC. So omega, remember, is the oscillation frequency. Because when we're talking about LC circuits, when you close this switch, these are effectively going to your capacitor is going to discharge through the inductor is going to be like, no thanks, and push it back. And it's going to kind of bounce back and forth and back and forth and back and forth. With that angular frequency, omega LC is 1 over root LC. So that's probably what we're going to be wanting to use here, because if we can see the voltage as a function of time, we can figure out the frequency that that voltage is oscillating. Okay, so I'm gonna measure, we know the capacitance, so I'm gonna measure the voltage so that I can figure out the oscillation frequency. Yeah, so we're going to briefly describe our method. So we are going to connect our charged capacitor. So we're going to close the switch. We're going to measure the voltage as a function of time across either the inductor or the capacitor. It doesn't really matter. We'll say inductor, sure. Across the inductor. And then we're going to use that voltage to measure the oscillation frequency, omega LC. Then we're going to repeat for different capacitors. Okay. So we know our capacitors, so I'm going to say probably need to measure our capacitors. So indicate quantities that can be measured. So this is going to count for both I and II. So we're going to close our switch. We're going to measure the voltage. We're going to use that to measure our oscillation frequency. And we're going to repeat for different capacitors. Okay. Indicate what quantities the students could graph on the horizontal and vertical axes to create a linear graph. So this actually is pretty much already set up for us. So if we compare that to y equals mx plus b, y equals mx plus b, I can put the oscillation frequency on my y-axis. On the x-axis, I can put 1 over root c. And then 1 over root L is going to be my slope. Okay, so my slope is going to be 1 over root L on an omega. Actually, I'll just write that out. On an omega versus 1 over root Z graph. Cool. All right, the end. That's it for A and B. Nice. Okay, so in experiment number 2, we are asked to use a graph to determine the inductance L2 of a new inductor. This time we're connected to a 12-volt battery, a 10-ohm resistor, and an initially open switch as shown in figure 2. After the switch is closed, the current in the circuit is measured at different times, and the corresponding rate of change of the current di dt is determined. The collected data are shown in the table. Curious. Okay, so we have the current and we have di dt. We're now dealing with an LR circuit. So 2 things we can do. Number 1, we can consult our equation sheet to see how I and di dt are related. Number 2, we can plot them on Desmos to see if we can figure out that relationship as well. So let's start with Desmos. Okay, so if we plot that data exactly as they gave it to us, so our x1s is our current and our y1s are our di dt, that is definitely a downward trend. Curious. No, it almost looks linear already. Okay, that already looks linear, so let's check it out. So if we do our regression, mx1 plus b, that looks pretty good. So our slope is negative 344.96. Okay, let's check out our equation sheet. Let's see how those guys are related. All right, so there's that di dt. There's my E, or my voltage. If I know the current, I could figure out the voltage. Oh, and there's that negative sign. Neat. That is definitely gonna be a linear relationship. Nice, let's go write that down. So for my RL circuits, I've got E minus L di dt. Now, really what we can end up doing here is we can do a Kirchhoff loop. A nice little Kirchhoff loop. So if I go meow, 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 I get my plus 12 volts. So I get my plus V of the battery. I go through my inductor. So I get that di dt. And then I get that minus IR from my beautiful resistor right there. So we've got I, we've got di dt. If I move one of those to the other side, so I get IR equals, I'm going to rearrange this a little bit, negative L di dt plus voltage of my battery. Okay, I'm going to divide by R just because I like having my left side isolated. So minus L over R di dt plus initial voltage. So this is probably going to be our relationship here. So if I put I on my y-axis, oops, I actually did that backwards over in Desmos. Shoot, that's fine. We'll switch them. So if I do I on my y-axis and di dt on my x-axis, that slope should be negative L over R, and the voltage of my battery should be V. So let me go switcheroo those Desmos values really fast. Oopsie doopsie, I just realized I forgot to divide V by R too. Good catch. Okay, so if we go switcheroo those, so V was 12, R is 10. If we come double check, we should have 1.2. That's about what it is. Awesome. And that's nice and linear. Great. So our slope in that case it's going to be that. Okay, let's carry on. So in part C, we want to label the axes of the grid provided with measured or calculated quantities, include units as appropriate. So it's up to y'all if you want to plot them as given or if you want to plot them switcherooed. So I'm going to put I on the y-axis because that's what I ultimately went with. That's measured in amps. I'm going to put di dt on the x-axis. And if you forget what the units are, they do tell you in the table. So amps per second. That's going to be amps per second. Okay. Now my current y-axis goes between 0.4 and 1. And my didt's go up to 280. So we need to scale these appropriately. So I need to go up to at least 1. So I can go by like 0.2, 0.4, 0.6, 0.8, 1. Yeah, that looks great. So 0.2, 0.4, 0.6, 0.8, 1.0, 1.2. And then on my didt, I went up to 280. So I could do like by 50s. So I could do 50, 100, 150, 200, 250, and 300 over here. And now we're just going to plot our data. So I don't want to keep scrolling. I don't want to keep scrolling back and forth. So I'm going to snag a little screenshot of that and pop it right there. Okay. Nice. Okay, so there was my data. Okay, so when we were 280, okay, there we go. Okay, so we plotted our data, and that is going to get us all of the points for part C. So we labeled our axes. We clearly labeled each axis with a numerical scale. We plotted our corresponding points. Great, and now we're going to draw our best fit line. So I'm going to draw you in pink. Yeah, that was great. Okay. Okay, so this is the part of the question where there's honestly really no reason you shouldn't get full credit for part C, even if you have no idea how the things are related, because you can go to Desmos. When we plotted just straight up the data that they gave us, let me switch my axes back. 1.1 and then nothing 10 to 300. So when I switch my axes back, like you should, like we plotted the data as is. That looks pretty dang linear. If I apply a linear fit to it, that r-squared value is nice. So you want to look at the general trend of it. It already looks linear. So just plot it exactly as they give it to you. Find the slope exactly as they give it to you. That's going to give you all the points for part C. Okay. All right. So we ended up doing it the physics way for my graph. But if you did it the just brute force way, your axes would be flipped. Your line would be a little bit different. Okay. All right. So now if we're going to find our slope by hand, we want to look for nice points where we can find our slope. So, but they have to be on our line. That's one of the biggest, we'll say no-nos that happens in the exam is students are trying to use actual data points. No, it has to be a point on your actual line of best fit. So I'm going to choose some nice intersection points. So you look nice right there. You look nice right there, Mr. 300 and 0.2. What's that? 4, 8.32. Okay, so 0.32. And as far away from each other as possible would be nice, because then you get a more accurate answer. That looks like a nice cross. It's near a data point, but it's not a data point. So that's going to be 50, 60, 70. Apparently I can't count today. That's problematic. And 1. Love that. So kind of close to our data point, but not exactly our data point. Cool. All right, so we're going to calculate our experimental value. So we said up here that if I plotted I from my Kirchhoff loop, if I plotted I versus di dt, then my y-intercept is going to be v over r, which was 12 over 10, which is about 1.2, which is about what we saw when we graphed it. Nice. And then my slope is going to be negative L over R. Slope equals negative L over R. Cool. So I'm going to write that down over here. So slope equals negative L over R. So we're going to find our slope using our good old y2 minus y1 over x2 minus x1. Boom, boom, boom. So 0.32 minus 1.0 over 300 minus 70. I don't have my calculator. Let me bust out my handy dandy calculator. All right, that's the slope we get if we pop that in our handy dandy calculator. Okay. The units for that, so my y coordinates were amps, so it's going to be amps. My x coordinates were amps per second, so over amps per second. That's going to leave me 1 over seconds, so that's going to be units of seconds. Okay. If you decide to use Desmos for your regression, you just need to make sure you write a note regression on calculator or Desmos, one or the other. You just need to tell us that's where you got it from, so we know you're not just pulling a number out of your butt. Yeah, really. All right, so if I do my Desmos points, my axes are all dumb, but whatever. We got 0.002887. 0.2887. Equals negative 0.00287. Right, so pretty close if we did our crappy by hand graph versus our more accurate Desmos regression. Yeah. All right, so we said our slope was equal to negative L over R. So M equals negative L over R. If I'm going to solve for my L, my inductor, I'm going to multiply that R to the other side. So R times my slope, not mass, just to be clear, and then divide by -1 or multiply by -1. All right, so I'm going to take my slope, I'm going to multiply it by my resistor, which was 10, and flip the sign. So that's going to be bloop. If I use my personal value, it's going to be 0.029, and we'll round it to 6. Okay, Henries. That should be Henries. Henries? H's? Henries. Yeah, or 0.02887. Since we have slope was seconds, resistor is ohms, ohm seconds is a Henry. Yeah. Yay, we did it. Go team go. Or you could say 29.6 millihenries would also be fine. Cool. The end.